RSM PDT-D high-strain pile bearing tester teaching video. 1. Device description. PDA host, high-strain testing cable, strain transducer, piezoelectric accelerometer. In addition to the host and supporting accessories, sensor installation tools such as electric drills, expansion bolts, and wrenches should be prepared for high-strain PDA testing of foundation piles. 2. Applications. The instrument is suitable for testing the vertical compressive bearing capacity and pile integrity. Monitoring the pile body stress and hammering energy transfer ratio during driving of precast piles provides a basis for selecting pile driving parameters and pile length. For large diameter expanded bottom piles and large diameter cast-in-place piles whose estimated QS curve has the characteristics of gentle variation, this method should not be used for vertical compressive bearing capacity testing. When testing the vertical compressive bearing capacity of cast-in-place piles, it is necessary to have on-site testing experience and reliable comparison and verification data under similar conditions in the region. Applicable standards. Standard test method for high-strain dynamic testing of deep foundations, ASTM D494517. Standard test method for low-strain impact integrity testing of deep foundations, ASTM D588216. The high-strain pile bearing test is a type of dynamic testing method to induce the resistance of the surrounding soil and the supporting force of the pile end in case of sufficient relative pile soil displacement when the impact pulse is spreading downwards after the pile top is impacted with a hammer. By applying a high-energy impact load on the pile top, measure the force and velocity signals. Calculate the integrity and the ultimate axial compressive bearing capacity of the tested pile with the wave theory, or select the pile type and length. Monitor the working efficiency of the pile hammer and the maximum hammer stress on the pile body of the driven pile. 3. Operation preparation. 1. Collect the pile soil information and geological exploration report. 2. According to the bearing capacity of the pile, choose a test hammer with an appropriate weight. Specification requirements. When the high-strain method is used for bearing capacity testing, the weight of the hammer is generally not less than 2% of the design value. The hammer should be symmetrical in shape, and the ratio of height to diameter, width, should not be less than 1. 3. Choose the right pile pad. The pad size should be slightly larger than the pile top section size. The pad can be made of wood or plywood with a thickness of 10 mm to 30 mm. When the hammer weight is light or the hammer fall distance is low, a thinner pad should be used. When the hammer weight is heavy or the hammer fall distance is high, a thick pad should be used. The thickness of the pile pad can also be adjusted according to the signal curve of the first hammer. When only the structural integrity of the pile is tested, the weight of the hammer should be reduced, the drop distance should be reduced, and the thickness of the hammer pad should be reduced. But it should be ensured that the obvious reflection signal from the bottom of the pile can be tested. 4. It is recommended to use a special high-strain hammering system that integrates the heavy hammer, the guide frame, and the hook, and can fix the free-falling track of the heavy hammer. Can ensure site safety, reduce hammer eccentricity. 5. Set up a safe area and establish a working surface. The testing site should be dry and flat and can meet the traffic conditions of large hoisting equipment and the requirements of hoisting operations. If necessary, the road surface and foundation should be reinforced. During the test, there shall be no construction projects that generate vibrations around the site, such as dynamic compaction, vibratory rollers, large lifting equipment, etc. Excavate the soil layer where the sensor on the pile side is installed. 4. On-site operation. 1. When testing pre-stressed concrete pipe piles, if conditions permit, try to select piles with flanges on the top of the piles for testing. If the pile head is damaged, the damaged section can be cut off, but make sure that the cutting surface is level and smooth. For test piles without flanges on the top of the pile, the test can be carried out only after the top of the pile is chiseled. When testing cast-in-place concrete piles, the pile head should be treated by increasing the length of the pile as much as possible. That is, connecting a pile section with a length of 1.5 to 2.0 times the pile diameter at the top of the original pile, which can greatly improve the quality of the collected data. 2. Sensor installation location. The sensor needs to be symmetrically installed on the pile side surface not less than 2D from the top of the pile and not less than 1D for large diameter piles. When installing, keep away from non-uniform places such as piling, welding, or area changes, and the installation position should be greater than 1D below it. Avoid installing into cracks. It should be installed on the ground or above the water surface while ensuring that the sensor connector is above the water surface. 3. Sensor drilling position. First, determine the installation position and the drilling position of the accelerometer, and then determine the drilling position of the strain transducer. The centers of the two strain transducer holes should be on the same horizontal as the accelerometer holes, and the distance between them should not be greater than 80 millimeters. The distance between the two strain transducer holes is 76 millimeters, and the line connecting the two holes should be parallel to the pile axis. The connection line of the accelerometer holes on both sides of the pile and the connection line of the strain transducer holes on both sides of the pile should pass through the center of the pile. 4. Handling of sensor installation location. For cast-in-place piles, the grinder should be used to smooth the mounting surface of the sensor, and the mounting surface of the sensor should be parallel to the axis of the pile. For pre-cast piles, optional smooth surface installation. 5. When drilling, the drill bit should be kept vertical to the side surface of the pile. 6. Expansion bolts should all be buried in the pile body. The installed expansion bolts should be in close contact with the pile body to ensure that the deformation of the pile body can be truly reflected on the sensor. 7. Put the pile pad on the pile head. 8. Install heavy hammer and guide frame. Guide system installation requirements. The base is stable. The center of gravity of the hammer coincides with the center axis of the pile. The reason why the guide frame and the heavy hammer are in place first, to prevent the impact damage to the installed sensor or the damage to the sensor cable, pressure break, etc. due to the imposition of the guide system. 9. Install the sensors. When installing, it should be noted that the surface of the pile body where the sensor is installed should be flat. The installation must be firm to ensure that the sensor does not slide relative to the hammer during the hammering process. The center of the strain transducer and the center of the accelerometer should be on the same horizontal line. The sensitive axis of the sensor should be parallel to the central axis of the pile. During the installation of the sensor, the initial deformation value of the sensor should be monitored. The initial deformation value of the installed strain transducer should not exceed the specified value. 10. Connect the host and sensors correctly. Connect the 19-core high-strain testing cable to the interface of host, and connect the acceleration sensors, 4 cores, to number 1 and number 2 interfaces of the end of the high-strain testing cable. Connect the strain transducers, 6 cores, to number 3 and number 4 interfaces on the other end of the cable, respectively. 5. Host introduction and settings. 1. Open the host and enter the main interface. There are 5 main function buttons on the main interface. High strain sampling, sampling in low strain RSM mode, and sampling in low strain PIT mode, export data and delete data. At the top of the screen are the current instrument time, electricity. The bottom is the Set, Update, and About buttons. You can set the time, screen brightness, screensaver duration, interface style, upgrade the sampling software, view software-related information, and repair information. 2. This instrument has two uses: low-strain PIT testing and high-strain PDA testing. RSM mode and PIT mode are low-strain sampling modes. When performing high-strain sampling, click the High-Strain Sampling button to enter the high-strain data sampling interface. The upper part is the curve display area, and the lower part is the parameter area and the operation command area. Parameter section. Project, P. It is the project site where the current file is located, which also corresponds to the name of the folder. File, F. It is the file name used when the current signal curve file is stored. Test L, L. It stands for the value of test L set by the user in the setting menu. Test V, C. It stands for the value of test V set by the user in the setting menu. Test CSA, A. It indicates the test CSA value set by the user in the setting menu. Interval, T. It stands for the sampling interval. Test row, D. It stands for the test row value set by the user in the setting menu. JC. It refers to the value of case JC set by the user in the setting menu. 3. Click Set to enter the parameter setting interface, which is divided into Common Settings and Sensor Settings. Common Settings. Project, pile number. The plus and minus signs on the right side of the pile number can be used to increase or decrease the previous pile number by 1 respectively. Set the value of pile L, test L, embed L, sounding based on relevant on-site data. The requirements are that pile L is greater than or equal to test L, is greater than or equal to embed L, is greater than or equal to sounding. When the input value does not meet the requirements, a prompt box will pop up. The range of pile L, test L, and embed L is 0.01 to 150.00 meters. The range of sounding is 0.00 to 150.00 meters. Set the pile CSA, test CSA, and PTO CSA based on relevant on-site data. The shape of the pile can be selected in each interface, and the cross-sectional area can be automatically calculated by entering the relevant parameters. Set pile row, test row, pile V, test V, diameter, hammer W, drop H, design KN, safety C, and case JC according to the testing requirements. Select the case method. The case JC input interface provides reference value data for reference. Click More Settings to set the testing unit, tester, and remarks. 4. Click Sensor to enter the sensor parameter setting interface. A1, A2, E1, and E2 represent the channels marked 1, 2, 3, and 4 connected to the high-strain testing cable, respectively. A1, A2 correspond to the piezoelectric accelerometer parameters of PDA test. E1, E2 correspond to the strain transducer parameters of PDA test. Each sensor setting includes the sensitivity coefficient, multiply, and the choice of whether to active in the calculation. The sensor sensitivity coefficient should be entered according to the data provided in the calibration certificate or factory certificate. Filter settings. Set FH pass, FL pass, VH pass, VL pass respectively. The purpose is to filter and pre-process the collected signal so that the collected signal is smooth without interference and can better meet the analysis requirements. It is generally recommended to set the H-pass to 0 Hz and the L-pass to 1000 Hz. Set interval, delay point. During high-strain on-site sampling, the interval is recommended to be selected in the range of 50 US to 200 US and adjust according to the pile length. The purpose of setting delay point is to adjust the position where the sampled signal is displayed on the screen. This parameter can only be set valid before sampling. The recommended number of delay point is 128, no need to modify. The purpose of setting the trigger level is to avoid the impact of other on-site interference on the test. According to the size of the interference in the on-site environment, select different trigger levels to reduce the impact of external vibration or noise on the collected signal. Avoid false triggering during testing. The trig level is divided into 4 levels, of which level 1 has the lowest trig level and level 4 has the highest trig level. It is generally recommended to set it to level 2. It should be noted that the smaller the trig level is, the easier it is to trigger, and the easier it is to collect signals. But it is also easier to cause false triggers due to interference signals. Set trigger CH and select the corresponding accelerometer as the trigger sensor. It is recommended to select any A. Click OK to return to the main interface of high-strain data sampling. 6. On-site data sampling. 1. Click the Monitor button in the Operation Command section to enter the monitor interface. According to the color of the last 2 round indicators in the Parameter section, judge whether the currently connected strain sensor is balanced or not. The first circle represents the state of the strain transducer number 3 connected to the high-strain testing cable. The second circle represents the state of the strain transducer number 4 connected to the high-strain testing cable. The red indicators mean that the strain transducers are not well balanced, for which the cause needs to be checked in time. Otherwise, the signal will not be sampled. The yellow indicators mean that the strain transducers are unbalanced and deformed severely, and the strain sensor needs to be reinstalled. The green indicators mean that the strain transducers are properly balanced. Adjust the installation state of the strain transducers according to the color of the circle until both signs are green. That is, both strain transducers are installed in place and in good condition. Click Stop to terminate the monitor state. 2. Click Sample to enter the signal sampling state, and the words "Waiting for hammer drop" are displayed in the curve area of each sensor. Although high strain is a non-destructive test, it generally does not have multiple hammering conditions. By tapping the piezoelectric accelerometer slightly, it can be confirmed whether it can be triggered normally and the signal can be collected before the on-site test. 3. Raise the hammer to the set height. Note that the low impact of the heavy hammer is the basic principle to ensure the accuracy of the high strain method to test the bearing capacity. Click Sample to enter the signal sampling state. The heavy hammer hits the pile head to generate an excitation signal, and the current signal curve is obtained through the sensor installed on the pile side. Click Pause to pause the sampling status. In the pause state, you can click Origin in the Operation Command area to convert to the FZV display interface and view the FZV curve at any time. Parameters can also be modified in the pause state. When you click Sample again, the newly acquired signal curve will be collected with the modified parameters, and the acquired signal curve will also be calculated with the modified parameters, and will be stored in the current file as the data of the same pile until you click Next Test. 4. Click Next Test to end the signal sampling of this pile. 7. Data viewing and on-site analysis. 1. During the sampling process, the host will save the original data of each hammer hit in real time. Click File to open the data. Click the Origin FZV button in the Operation Command area to make the curve displayed curve alternate between the original curve and the FZV curve. The high-quality data curve appears as 1. The time of force and velocity are the same. The two coincide before the rising peak, and the two are coordinated after the peak. The F curve should be above the ZV curve unless the pile body is defective, and the distance between the two curves increases with the increase of the soil resistance on the side of the pile. If it increases, the difference is equal to the total resistance value of the corresponding depth, which can truly reflect the actual situation of soil resistance around the pile. 2. The end lines of the F curves and ZV curves are zeroed. The displacement curve converges to the time axis. 3. There is no serious eccentricity in the hammering. The test signals of the two symmetrical forces or speeds should not be too different, and the two sets of force signals will not be pulled. 4. The test curve is smooth. There is no obvious high-frequency interference clutter, and the reflection on the bottom of the friction pile is clear. 5. There is enough sampling length. Ensure that the length of the curve fitting time period is not less than 5L divided by C, and the duration is not less than 20 milliseconds after 2L divided by C. 6. The penetration is moderate. Generally, the single-click penetration should not be less than 2 millimeters, nor should it be greater than 6 millimeters. 2. Click the Zoom button to zoom or expand the currently displayed curve. Click Browse to display the signal curves of all files in the current save path in turn, and the F area will display the file name of the open file in real time. Click the Graph button to enter the graph interface. Click FVWWUD, ACC, Velocity, Display, Strain, Force, Energy, Tension. There will be corresponding curve display in the curve display area. Each curve can be shifted left, shifted right, and zoomed. 3. Click the Analyze button to enter the analysis interface. The upper part of the analysis interface is the curve display area and the pile schematic display area, and the lower part is the parameter area and operation command area. The far left of the operation command area is the hammer quantity information in the currently viewed data, including the total hammer count and the currently viewed hammer count. Click plus to select the subsequent hammering signal in sequence. Click minus to select the previous hammering signal in sequence. Fix L, Fix V. Click the button to switch between Fix L, Fix V in turn and cycle. When Fix L is displayed, it means that the current analysis is performed in the Fix L mode. That is, the velocity is calculated based on the fixed pile length. On the contrary, when Fix V is displayed, it means that the current analysis is performed in the Fix V. That is, the pile length is calculated based on the fixed velocity. Top, bottom, defect. When it is displayed as top, the host will automatically find the maximum peak value of the ZV curve in the curve display area as the pile top. You can adjust the position of the pile top in the signal curve by clicking left shift and right shift. At the same time, in the pile diagram area below, the position of the pile top will also be adjusted accordingly. When it is displayed as bottom, the host will automatically find the position of the pile bottom according to the pile length at the present testing point and the preset pile velocity. You can adjust the pile bottom in the signal curve by clicking left shift and right shift. At the same time, in the pile schematic area below, the position of the pile bottom will be adjusted accordingly. When it is displayed as defect, select the position of the defect between the pile top and the pile bottom, and adjust the exact position of the defect by clicking left shift and right shift. At the same time, in the pile schematic area below, the host will automatically identify and calculate the depth of the defect to the sensor installation point. Click Method to select the appropriate calculation method for the bearing capacity of foundation piles. Click JC, adjust the JC value, and check the calculation result of the bearing capacity of the foundation pile. Click L-Pass, H-Pass button to filter the curve. The processed curve needs to redetermine the pile top, pile bottom, and defect position. 4. Data export. In the off state, insert the U-disk into the USB port of the host. Open the host, click Export Data on the main interface. Select the file to be exported and click Export.